is 118. Let's go back to talk about crystalline representation and semi-stable representations. So let's quickly recall, we have constructed two functors. Decrease from the category of crystalline p-adic crystalline representations to the category of filtered phi modules over K, and respectively semi-stable representations could be coefficients of JK to filtered phi m modules. Actually, we have proved that those functors are feasible exact tensor functor. Okay, so now the first thing, let's quickly recall the construction of those functors. The definition. Well, firstly, let's look at those decrease so recall that firstly there is a covariant version and contravariant version. Right, so there are two versions. So the first version, covariant version using the tensor product, so it maps way to our decrease tensor over QP fixed point by JK. So the period ring corresponding to crystalline representation. For the semi-stable, we have similarly just instead of decrease, we have be semi-stable. So actually we haven't discussed in detail about the construction of be semi-stable, not yet. Actually we emphasize on the decrease crystalline representation. Okay, so second remark. Yeah, so let me also mention the dual version maybe, right? So the dual version is decrease with the same target source, but decrease way is defined to be home QP JK way decrease and DST star way defined to be JK equivalent BST. Right. Further recall, a p-adic representation V is called crystalline if and only if its dimension of decrease V as K0 vector space equals dimension V over QP respectively. V is semi-stable, if and only if dimension of dst V over K0 equals the dimension of V over QP. This is also equivalent to, respectively, equivalent to this alpha crease from B crease tensor decrease over K0 to injective. This is always injective. B crease tensor directly with V is isomorphism. Correspondingly, you could imagine for alpha st there is isomorphism. So actually this is what we define to be semi-stable, to be admissible, right? Which means with crystalline is equivalent to with B crease admissible. Why it's called semi-stable if it's B st semi-stable, admissible, sorry. Okay, good. Then let me add some remarks. Firstly, let's mention an important proposition without proof. For r bigger or equal than 0, the following sequence is exact. So start from 0, and then we got QP, and then phi minus R, P crease, Frobenius fixed, phi minus R, Bidoran. So Bidoran plus. Well, on Bidoran we have filtration, very clear, but on decrease the filtration comes from its embedding into Bidoran, right? Bidoran, the filtration is given by Bidoran plus times T power, passing to the limit. Into the direct limit, let's see. As r goes to plus infinity, we get the following sequence. The following exact sequence. 0 QP decrease Frobenius equals 1 Bidoran plus, because when r tends to minus infinity, as a reasonable filtration, this is always the whole space. Second remark. So maybe let me put 1.1. If we set r equals 0 in the above remark 1, then what do we got? We got QP equals, and then this field 0 is Bidoran plus equals field 0 B crease Frobenius equals 1. as corollary of that, right? Remark 2. So let V be any semi-stable p-adic representation of GK of dimension H. Let D equals semi-stable V. We want to construct a covariant functor which we will call VST. So reverse the arrow, right, from the filter find modules to semi-stable to semi-stable representations, but let's start with at least the GK module such that VST composed with DST, a way isomorphic to way, right? And then recall that we have our alpha ST, which is isomorphism when we is semi-stable representation. This is PST linear Frobenius compatible. Monodromy operator is also compatible. Also, this alpha ST K is a filtered isomorphism. FSDK means tensor is K. So let's denote this by X. Then let V1, V2, Vn, and omega 1, omega 2, omega n be a basis of V over QP respectively of D over K0. So why not write filter find module over K0 then? Wow, we write filtered find module over K. Why not denote it over K0? And so both if we just extend by tensor 1, so let's say identify vi with one tensor vi, then this become a basis of that tensor product. Correspondingly, omega I with one tensor omega I, then they are both basis of X over BST, coming from different isomorphism. And then any element of X can be written as a sum of B tensor omega, where B is from BST, omega from D, or as C tensor V with C in BST, V. And let's look the actions. So the JK action for Frobenius and monodromy X, then it could be written as follows. So J acting on B tensor omega, because it's fixed by J, then this is only JB tensor omega. The semistable is fixed by construction. And C tensor V, so then there are Galois action on both sides. Good. Secondly, let's look at Frobenius. So Frobenius semi-linear. While Frobenius is trivial on Galois representation, there is in priori no Frobenius there, so put identity. Lastly, the monodromy acting on B tensor omega is again semi-linear, and again there is no monodromy put on the Galois representation, and so we put identity. X also has a filtration. And then by the map, X map to Y tensor X, we have inclusion as follows. So we start with X, and we map it into XDR, defined to be p-adic tensor. We extend from BST to p-adic. This is hence isomorphic also to both to tensor with decay over K0 and tensor with V over QP. And the filtration is given by or reduced from filtration of B the RAM tensor over QPU is way, which is R plus S equals I, fill R, B the RAM tensor with fill S, DK. So this is a standard construction filtration when you have tensor product of two space with filtration. Now we can also construct a function as follows. So we can construct a V of ST over DST away, defined to be those XC, small xc that tensor product of D with BST. So let me recall this is. Such that fixed standard Frobenius and killed by monodromy and lies in filtration 0. This is the same as saying fixed by Frobenius, killed by monodromy, lies in field of 0, extra. What is extra? Extra is what we just constructed. So the field 0 of X, yeah, U the filtration be the RAM, or use the filtration BST, but the filtration BST should again comes from the filtration be the RAM. Yeah. So it's the same. Notice that. So recall D is DST away. Notice that W is contained in WST DST away. And this one tensor will satisfy those conditions described here. Let's check it in more detail. So exercise. Let me just put this as exercise. Exercise. Check that. So WST, DST, way, isomorphic to way. So So let's write element x into the form n bigger or equal to or less equal than h bn tensor vn as element of vstd. So d is recall dsty, where small b in bst and d equals dst away. Notice that n of x equals, by definition, n of bn tensor over vn, and so this is 0. I mean, we want to do is take x here and we prove it's in V. So let's take element here, write in the general form, and so by the definition this have to be 0, and so when this is 0, this implies that this n bn equals 0. Because there's one tensor V and forms the basis. This is again our basis. This is like linear combination of basis equals 0, so all the coefficients 0, and then this is telling that this small n is in decrease because those killed by monodromy in BST is decrease. Did we mention this or not? N equals 0 of BST is decrease. So one thing is that the crystalline representations corresponds to the filter phi module, or you could also say filter phi module with n equals 0. This also tells you intuitively those killed by n inside BST should be decrease. Not sure we have mentioned this or not. Should have mentioned this. The monodromy operator on period rings. Okay, so let's just continue with this. So this works for any n bigger or equal than 1 less equal than h. Similarly, we have also the second condition, phi x equals x. So this implies I'm going to apply the formula from 1 to h. Phi of bn tensor vn, because there is no Frobenius action on collection, equals bn tensor vn, and so again, this for the same reason, telling you that phi Bn equals Bn for all n, and so Bn lies in fixed points. Fixed points of under Frobenius fixed points of BST. Yeah. Right. Wait. Yeah, you could see that. Lastly, we have the condition. X is in field 0 of X term. This implies that this Bn lies in field 0 beta plus, again for any n bigger equal than s equal than h. And so by the result I mentioned at the beginning, here. So sometimes we call this fundamental exact sequence. So by the fundamental exact sequence, imply that Bn is in B drum with, let me see, field 0 of decrease and Frobenius fixed field 0. Yeah, because you're satisfying both this condition. In particular, you are in field 0 of B crease, because B crease intersection field 0 B drum is filtration B crease and Frobenius equals 1, and this is Q. Nice. Therefore, X lies in QP tensor QP way inside way. By the semi-stable isomorphism, we then conclude that an isomorphism. Remark, equivalently, we could also could define directly BSTD to be field 0 BST Frobenius equals 1. Let D tensor over K0 with BST. Also, monoidromy operator equals 0. You could also write this as the kernel of BST tensor K0D n equals 0 from this equals 1, and then map to quotient of this bit around, let's see, quotient by field 0 of it. So it's lies inside it, which means just quotient by the filtration 0. So exercise, this is exercise 2, proposition. The exact tensor functor dst from semi-stable representation to filtered phi mod u over k is not only faithful exact tensor but fully faithful with inverse its essential image given by the functor VST just constructed. The same holds for contravariant using VST contravariant defined to using the whole compatible with filtration Frobenius monodromy BST. This means Frobenius, compatible, filtration compatible, monodromy compatible. Proof. We know, actually we proved that before. DST is faithful, exact tensor functor. Now we show it's fully faithful. So suppose V1 and V2 are semi-stable. P-adic representations of GK. And let D1 equal DST of V1 and D2 equals DST of V2 in MF filter phi modules. Let's start with 2 filter phi module. For F any map in the category filter phi module over K, we need to show that there. This map. We want wait. Such that DST takes this map to F. Right, so we have F on this side, and we have to show that there is such a map. And when you apply the functor DST, we got this. This is showing that DST is fully feasible. Because what we are doing is you're showing that it's full. I already show it's feasible. You have to show its full functor. So home gives you surjective map. Now by the semi-stable comparison theorem or isomorphism, so we have mentioned before. Let me recall. This one. So the BST linear extension, let's write one tensor F from BST D1 to BST D2 is identified because we have this isomorphism. Is identified with some BST linear GK equivalent Frobenius compatible monodromy compatible morphism. Let's call it F tilde. This is from BST V1 to BST V2. So we use this comparison isomorphism as a bridge, and then we have to move that structure, extra frameworks, right? Explicitly this F tilde is just apply this Yeah, exactly. This, if you want, you could draw even a diagram. Right, so now the map F2 respects the formation of the phi fixed parts in field 0. In other words, this BST linear map must carry V1 into V2 by GK equivalent map. Hence, this F tilde is BST scalar extension. Of some J from V1 to V2 in the representation side. So this is isomorphism compatible with many structures for any small roommate collection. Which means that again you just start with this F tilde and then you apply the field 0 and then you apply fixed point under Frobenius and then you apply monodromy. This is compatible, but then this gives you back V1. Right, for a similar reason what we have computed before. For a similar reason. I mean, you could take those because it's compatible with those structure. Good. So now by functionality of the semi-stable comparison isomorphism, we get this map. We by the functionality of the semi-stable comparison isomorphism, we conclude that this one induced exactly by DST to the one we started with, and so prove the free faithfulness.